Okay, the system doesn't stop here. Let's continue and then let's now average the motion of the inner binary. So this is the perturbation Hamiltonian averaged in the outer binary. Let's now average in the mean anomaly of the inner binary. This turns out to be a more complicated task. But the main result is going to be that by the average procedure itself, we're going to get rid of the mean anomaly of the inner binary. Then that means that the double average of the Hamiltonian does not depend on the mean anomaly. So that means that the energy is also constant. The energy, which means then the semi-major axis of the inner binary is going to be constant. So these are the two conserved quantities in the Kozai-Lidov oscillations. We're going to see that you cannot get rid of the argument of pericenter. So the angular momentum is not conserved, but the energy and the vertical component of the angular momentum are, because the averaged out got rid of the longitudinal descending node, and the process of averaging out will, by definition, get rid of the dependency on the mean anomaly. Now we saw that the vertical component of the angular momentum, LZ, meant a relationship between the semi-major axis, the eccentricity, and the inclination. If the semi-major axis is also constant, that means that the quantity that is constant in here is a combination of the eccentricity and the inclination alone. So the system allows for the inner binary under the perturbation of this distant third body to exchange eccentricity and inclination, as long as the product given by this quantity remains constant. These excursions in eccentricity and inclination are the Kozai-Lidov oscillations. So let's see the averaging procedure for the inner binary. First, we have r squared and r1 cubed. So the outer orbit is circular. So we can substitute r1 cubed by the semi-major axis of the outer binary and multiply and divide it by the semi-major axis of the inner binary. And we can expand r over a in terms of the mean anomaly. We can approximate r over a squared as 1 minus twice the eccentricity times the cosine of the mean anomaly, plus this curve of 2 times 3 minus cosine of 2m. That's an expansion to second order in eccentricity. Now, the other term that depends on the mean anomaly is the sine square of omega plus f, which you can expand as. Now, it would be tempting to average out the sines and the cosines of the true anomaly, but you cannot, because the true anomaly is a nonlinear function of the time. It is the mean anomaly that is a linear function of time. You need to expand the cosines and the sines in series of the mean anomaly. This would be a long exercise in algebra. I'll simply quote the result. So as promised, the argument of pericenter does not cancel out from the Hamiltonian. So the system indeed conserves energy, conserves the vertical component of the angular momentum, but it does not conserve angular momentum. That means that the inner binary can exchange angular momentum with the outer binary, although they conserve the vertical component. The energy, which is the semi-major axis of the inner binary, remains constant while the system executes these oscillations between eccentricity and inclination. This illustrates here how these oscillations will play out. You can pass from an orbit of high eccentricity and little inclination to a highly inclined orbit and small eccentricity, or vice versa. You can start from this nearly polar orbit, very high inclination but small eccentricity, and exchange some of this inclination for eccentricity while conserving the vertical component of the angular momentum and keeping the semi-major axis constant. And in this case, I said, the three particles can be in many different configurations. The central body can be the Earth, the perturbing body can be the Moon, and the test particle, the massless one, can be an artificial satellite. Or the main body can be the Sun, the perturbing body Jupiter, and the massless one can be an asteroid, for instance. Two of the many possible applications. This here also shows how exactly this conservation of the vertical component of the angular momentum is happening. You have here, say, the angular momentum of the inner binary, and here the angular momentum of the outer binary, and they combine into this total angular momentum. Is this total angular momentum that is being conserved, not the angular momentum of the inner binary. What is conserved is the projection of the vertical component, so that combined, the angular momentum of these two orbits, the inner and the outer, combine into a total angular momentum that itself is conserved.